Okay, let's continue now with our discussion of entity relationship data modeling. Now, before we do that, let's take stock of where we are in our discussion. So, the setting that we have is one where we have a business application. The example that we're using is an airline reservation application. Let me pick up the laser pointer here. So, the application that we're looking at is an airline reservation application. This is the one that we've been using as a prototype for our discussion. So we have something, the business application that the customer, the end user sees, and the discussion that we are having is really how do I describe the structure of the underlying database? And the tool that we are using to describe that structure is the entity relationship model. And the process of modeling starts with some description of the narrative description of the business application, from which we go through a process and we end up with the entity relationship data model. It's a pictorial representation of the structure of the database, and the discussion that we have had so far is what are the symbols that are used in drawing that data model, that structure, and what do those symbols mean? What are the concepts underlying those symbols? Just to refresh your memory, some of the important concepts that we introduced were the concept of an entity, the concept of a relationship, and then we refine those concepts further. For instance, entities have attributes, those are properties of entities. Relationships have properties called cardinalities. They tell you how instances of one entity are related to instances of another entity, and we talked about minimum cardinalities, maximum cardinalities, etc., etc. And then from that, we identify three different types of relationships: one to one, one to many, many to many, and so forth. So we are gradually introducing various building blocks, concepts, as well as the associated symbols with them that go into constructing the structure, the entity relationship model itself. Now, in this discussion, in this lecture, we will further refine those concepts, that we'll introduce more symbols, we'll introduce some more refinement of the concept, and we are doing this not for the sake of complicating the discussion, just introducing unnecessary complication. The fact is that real life data is messy, and real life applications, business applications or otherwise, have complications, have nuances, have characteristics that if we want to capture accurately, we need more constructs and tools. So just to give you a simple example, let's come back to this reservation example that we're using. Just take this entity called aircraft. In the discussion that we've had so far, we had informally said that one of the entities in this airline database would be something called an aircraft. But I think you can easily understand that all aircrafts are not the same. The different categories or subgroups of aircraft. There are wide-bodied aircraft, there are narrow-bodied aircraft, there are long-haul aircraft, there are short-haul aircraft. And while all aircraft share certain properties, there are differences among the subgroups. So you can see nuances. Same thing goes with route. Okay, yeah, all routes have certain things in common. For instance, how long is the route, etc. But there are different categories of route. For instance, there are domestic routes, there are international routes. Why? And there are differences among them. For instance, if the international route goes over the water, for instance, the Atlantic Ocean or the Pacific Ocean, then only certain types of aircraft can fly on those routes. Okay? So there are nuances to this data. So just using the constructs that we have introduced up to now, while those constructs are important, they are absolutely fundamental, like entities, relationships, cardinalities, and so forth. We need to refine that thinking a little bit more in order to be able to do a good job of representing the structure of real life business applications. So we are in this discussion, we are going to continue from where we left off in the last class, the last lecture, and we will introduce more concepts associated with entity relationship model. We'll try and understand what they are, and we'll see examples of what those additional constructs are. Specifically, the additional concepts and constructs that we'll be introducing. Here's the list. Well, we'll introduce this concept of relationship attributes. Uh, we'll introduce the concept of relationship degree. These are refinements of concepts that we've introduced so far. Generalization, specialization, and we will discuss all of these refinements through examples. So that's our agenda for this particular lecture. So let's first look at this thing called relationship attributes. So far in the discussion, so far, like in the last lecture that we had, what have we said? We said that okay, we have this thing called an entity. In this case, for example, student, and every entity has properties or attributes that we store information about. Like, so for the student in this case, we store the student's G number, the name and address and email of the student. So these four things are attributes of entity. Okay, and it's pretty natural to think of attributes of entity. That concept comes very naturally. Anything about which you store information will have properties about that you want to store data. Okay, however, relationships can also have attributes. So there are properties that are associated with relationships. Okay, so just to give you a specific example, here we have a relationship between student and offering. And if you think back to constructs that we introduced in our last lecture, what do these pictures tell us? This is just a repetition of something that we've discussed in the last lecture, but just to reinforce, I would say in words, one student enrolls in at least 0 offerings and at most many offerings. And in the reverse direction, one offering enrolls at least 0 students and at most many students. So that's the relationship between student and offering. It's a many-to-many relationship, something that we have seen in the previous lecture. But this relationship called enrolls, it doesn't just tell us that student is taking various offerings. It has some, it can have properties associated with it. For example, take this property called final grade. So it's an attribute. It's a grade A, B, C, D, whatever the grade might be. But just think about it. A grade is not a property of a student. A grade is not a property of an offering. It is a property of the combination of student and offering, meaning it's a property of the relationship between student and offering. So a student enrolls in a particular offering and gets a final grade in that offering. Okay, so the data for final grade, this attribute called final grade, is relevant only when a student enrolls in an offering. So it's relevant only for this relationship. So it's a property of the relationship. So I hope you understand this distinction about attributes that are properties of relationships. Properties, attributes of entities, these are very natural things that we can relate to. Properties of relationships doesn't immediately, intuitively appear in our mind, so it's worth reflecting on it and understanding that relationships themselves, not all relationships, but certain relationships can have properties associated with them. Here is another example. So just to repeat so that we reinforce our understanding of symbol, one order includes at least one product and at least many and at most many products. So that's what these cardinality symbols mean. Okay. So obviously you shouldn't have an order which has no product. So an order includes at least one product and at most many products. And if you go in the reverse direction, one particular product, any one product, is included in at least 0 orders and at most many orders. Obviously, you could have a product that nobody has ordered. So a product is included in at least 0 and at most many orders. So this is a relationship between order and product. It's a many-to-many relationship because if I look at the maximum cardinalities on both sides of the relationship, the maximum cardinality is many on this side, many on the other. So it's a many-to-many relationship. So all that's a repetition of what we discussed in the previous lecture. Now let's come to the relationship called includes. Okay? This relationship between order and product, that relationship itself could have some attributes, some properties. For example, quantity ordered. I hope you understand that the quantity ordered, that attribute makes no sense just if I think of just the order by itself. It only makes sense if I think of the order and the product in the order. So I ordered 10 units of this, of let's say, some meat product. Okay, and then there is unit price. Okay, so one could make the argument that the product itself has a list price, but the price actually charged on the order varies with the order. So there could be a discount, for example. So if you take these three properties, quantity ordered, unit price, and discount applied, you can easily understand that the business circumstances might be such that these are properties of the relationship. They are not properties of any one entity in the relationship by itself. Okay, so this is these three attributes that you're seeing here, and another examples of relationship attributes. So these attributes, so these three, are relevant only when an order includes a product. So when you have a product in an order, that's when those three attributes are relevant. Okay, so this is what we mean by relationship attribute. So you can see this concept of an attribute has been refined to now apply to relationships as well as entities. The appearance of attributes in entities is very natural, that we've said repeatedly many times so far. But attributes can also be properties associated with relationships. So that's one refinement that we're introducing from the previous lecture. The second refinement that we will introduce is something called relationship degree. So in the previous lecture, we talked about cardinalities of relationships. This is something slightly different. This is something called relationship degree, and it's associated with how many entities are involved in describing a relationship. Now, I would venture to say that 90% of the time in real life setting, you will encounter relationships that connect two entities. But that's not the only type of relationship that can arise. There are situations where certain other types of relationships can arise. So it's something different from two entities being connected to one another. So let's see what those variants might be. So relationship degree, the degree of a relationship is how many entities are involved in the relationship. As I just said, 90% of the time, the vast majority of relationships that you will encounter are binary relationships. So if you look at a real life business application and you're trying to construct the structure of the corresponding database that will support the business application, you go through the process of identifying the entities that are there in the business application, and then we are going through the process of identifying relationships. Bulk of the relationships will be binary, meaning they will connect two entities. So here are three different examples. One customer places at least 0 orders and at most many orders. One order is placed by at least one customer and at most one customer. That's what this symbol means. This is a binary relationship, and I just talked through what these symbols, the cardinality symbols, mean. This is something that we have discussed in the previous lecture. So look at the second example. This is also a binary relationship. So authors write books. So one author writes at least 0 books and at most many books. One book is written by at least one author. You can't have a book without an author. So one book is written by at least one author and at most many authors. Okay, so you can see the maximum cardinalities are many on the two sides. So this is a many-to-many relationship. Whereas the customer to order relationship is one to many. Okay. Last example, student and course. One student enrolls in at least 0 courses and at most many courses. One course enrolls at least 0 students and at most many students. So all these three examples that we just saw are all binary relationships. They have different cardinalities, as we just saw, but each of them is a binary relationship. Why? Because each of them connects two entities. That's what makes each of them a binary. However, that is not the only kind of relationship that can arise. You could also have what is called a unary relationship, meaning an entity related to itself. That may seem weird on the initially, but if you think through, you can think of examples of unary relationships. Okay? So basically, in contrast to binary relationships that we just saw a couple of minutes back, a unary relationship connects an entity with itself. That's why unary, one entity related to itself. So just one example over here. So you have employee related to itself. So you can see that the line, remember relationships are represented by lines. So here you have the line feeding back on itself. So and every relationship must have a name. That's something we mentioned in the last lecture. So here the relationship is supervisors. Okay, so one employee supervises other employees. So how do we read this line, this relationship? So as with all relationships, there are cardinalities associated with the relationship. The inner symbol is the minimum cardinality. The outer symbol is the maximum cardinality. Okay, so let's try and read through what this picture. So every picture, every entity relationship model diagram that you see will have symbols on it. It's a picture, but the picture tells a story of the structure of the database. It's a very precise representation of the structure of the database. So let's see what this picture is telling us. So I start as this. The narrative is the same. One employee supervises at least 0 employees and at most many employees. So visually, it's very easy to conceptualize this unary relationship. Just imagine that there is a copy of this entity called employee. So think of a copy of this box called employee. Just put it somewhere here in your mind and just connect the line one with the other. And then everything that we had discussed about binary relationship, you can use that same logic. So using that logic, this is how I read the relation, the cardinality. One employee supervises at least 0 and at most many employees. So not all employees are supervisors. Some employees don't supervise anyone. So one employee supervises at least 0 and at most many employees. Going in the reverse direction, one employee is supervised by at least 1 and at most 1 employee. So this is an organization. So if this picture is correct, this tells me that the organization is not a matrixed organization. So in matrixed organization, one employee could have multiple bosses. So let's say they're working on 3 projects, and each project has a different boss, a different supervisor. Then you could have an employee that is supervised by multiple employees. In that case, this picture would not be accurate. So I've said this repeatedly, and I'll say this several times again. The entity relationship diagram has to be a faithful, accurate representation of the characteristics of the business application. Okay, so if a business organization is matrix, and you could have an employee who could have multiple supervisors, then what this picture should look like. Let me see if I can pick up the pen here. If that's the case, then the picture would look like this. Okay, one employee is supervised by at least 1 and at most many employees. That's what the picture would look like. Okay, so this was an example of a unary relationship. Here's a second example. A product has other products. So you could have a product that has subparts in it. Okay, so if you think of a car's carburetor, for example, it's a product, but it has many different parts in it. So one product, so again to read the symbols, one product has at least 0 and at most many subparts, products inside it. Okay, and then in the reverse direction, you can read those cardinalities in a similar manner. So these two pictures, these two diagrams that you see are examples of unary relationships, a situation where an entity is related to itself. Another common example that would be familiar to you, if you think of course, okay, and I have, how can course be related to itself? The relationship is prerequisites. Now, as students, you all know that certain courses are prerequisites to other courses. Okay, so let's see how we would go in each direction. So we would say one course has, so I'm going in this direction now. One course has at least 0 and at most many prerequisites. So we all know that there are courses that don't have prerequisites. So one course has at least 0 and at most many prerequisites. In the reverse direction, one course, so I'm going in the reverse direction now, one course is a prerequisite for at least 0 and at most many courses. So here again is a very common example of another unary relationship, a course being a prerequisite for other courses. So I hope you see what's the distinction between binary relationship and a unary relationship. So here are other examples of situations that can give rise to unary relationship. For instance, a driver's license. Let me pick up the pointer here. So when a driver's license is issued to you, it has a driver's license number, issue date, and so forth. Now, when it is issued again, when it is renewed, that's still a driver's license, right? So a driver's license could be related to itself. It's a renewal of another driver's license. Same thing with the health insurance policy. If it's reissued every year, you could have the policy card being related to itself. So it's a unary relationship. So you would have, let's pick up the pen here. So you would have an entity called, let's say, health insurance policy card, and it would be related to itself through renewals. Okay, so there are different business situations. So I hope you're seeing why we are having to introduce these additional refinements of concepts that we have seen in the previous lecture, because situations arise in real life business applications that require us to be able to capture these kinds of relationships. So if we had stayed with only the constructs that we saw and the symbols that we saw in the previous lecture, we would have a difficult time constructing the structure of a database that will support this particular business application well. Okay, so these refinements are not being introduced just for the sake of introducing complication. They are being introduced to enable us to capture real life situations, the data and relationships within the data that actually arise in real life applications. Here's another example of a different type of relationship. So we talked about unary relationship, binary relationship, and here is a ternary relationship. It's a relationship that connects 3 entities. So if you think of, let's see here, my laser pointer. Okay, so if you think of a prescription, this thing, a prescription here, what are the attributes of a prescription? The prescription date, the dosage, the date field, number of refills allowed, the next refill date, and so forth. Okay, but if you think of these attributes about a prescription, so it's a prescription is a relationship among different things. A prescription is associated with the patient, it's associated with the doctor, and it's associated with the medicine. For instance, I changed doctors a few years back, and the same medicine that the previous doctor had given me, the new doctor that I was assigned to changed the dosage for the medicine. Okay, so a prescription in this case is a relationship between among 3 different entities: patient, medicine, and doctor. So this is not a unary relationship. This is not a binary relationship. This is a ternary relationship because it connects 3 different entities. Not just that, this is a ternary relationship that has attributes. Remember, we talked about relationship attributes a few minutes back. This is a ternary relationship which has its own attributes. So these attributes you see over here, date filled, refills allowed, and so forth, these attributes only make sense, only apply to the relationship among these three entities. These attributes do not apply to any one entity by itself. It only makes sense in the context of the relationship among these three entities here. Okay. Another example of a ternary relationship, you have customer, you have order, and we've seen a binary relationship between customer and order. Customers place multiple orders and so forth. And here you have a courier. Okay, so think of these. You have a relationship that connects customer, order, and courier. So an order is delivered by a particular courier to a particular customer. And if you look at these attributes over here, ship date, expected delivery date, shipment method, actual delivery date, weight, and so forth, these attributes are properties of the relationship among these three entities. Okay, so these attributes that you're seeing here, these are examples of relationship attributes. So think back to what we had said a few minutes back, that yes, attributes of entities, something very natural, we can all relate to it. Attributes of relationship doesn't come to us naturally, but it's certainly possible. Here you see an example of these 5 attributes. These are not properties of any one of the entities by themselves. These attributes only make sense in the context of the relationship among these 3 entities. And later on in some subsequent class, we will see how this is actually represented, implemented physically. For now, we are at a conceptual level, meaning we are trying to understand, express the structure of a database conceptually, trying to reflect that the structural needs that are evident from the narrative or the description of the business application. Okay. And the last refinement that we will introduce in this lecture is called generalization / specialization. They're sort of two sides of the same coin, and it's a refinement of our concept of an entity. We have introduced this concept of an entity in the previous lecture. The pictorial representation of an entity is as a box, so you already know that. Let me pick up the pen. So the representation of an entity is as a box. The entity will have a certain name, and there are properties, attributes of the entity that are listed within the box. This is something that we have already seen, okay? Things about which we store information. So this concept of generalization, specialization is a refinement of this particular concept. And let me go back to a couple of examples that I mentioned at the beginning of our discussion today, the airline reservation example. So the discussion that I had, the comments that I had made rather, was that yes, you have this entity called aircraft, you have this entity called route. So all routes have certain properties, all aircraft share certain properties, but not all aircraft are the same. There are certain natural groupings of aircraft, and some of the groupings that I mentioned were wide-bodied aircraft, narrow-bodied aircraft, things like that. Okay. Then for route data also, there are characteristics that are shared by all routes, but there are certain natural groupings of route. There are domestic routes, there are international routes. So I hope you sort of inferred from that discussion that entities also have some nuances to them. It's sometimes not possible or not convenient or not efficient to think of entities just as one big glob. Okay, for instance, an airline can think of all its passengers as a group of customers. Sure, it's an entity called customer. But very clearly, airlines have different groups of customers in mind. There are their elite flyers, the group of customers who fly a lot, they pay premium amount. There are gold cards, there are silver cards, and then there are the occasional flyers. So there are some natural groupings even within this entity called customers for an airline. There are natural groupings. So what I'm leading up to is that Entities are entities, but there are nuances within what we think of as an entity, and that's what we are getting into when we introduce this refinement called specialization slash generalization. Those are two sides of the same coin, really. Okay. So you could have situations where an entity might contain distinct subgroups of entities. Okay, subgroups have some attributes that are different and are not shared by the entire entity set. So, as some examples, you could have an entity called bank account. Okay, so let me get the pen. So you could have an entity called a bank account, and all accounts share certain common properties, like there's an account number, okay, the account holder's name, the date the account was opened, and so forth. So there are certain attributes, certain properties that are shared by all accounts. But you can easily think of certain subgroups of accounts. You could have checking accounts that don't have any interest rate associated with them. You could think of savings accounts that have interest rates associated with them. So these subgroups can have attributes that are not common. Okay, you could have a loan account, and you could have the interest rate of the loan and the date the loan is due. So again, uh, attributes that are not shared by the other subgroup. So you can see these little nuances that are cropping up. Uh, so you have an entity called account. So if you think of this entire group is an account, that's certainly we could do that. But there are some natural subgroups within this entity. Okay, so these little subgroups that you're seeing, these are considered specializations of this generic entity called an account. So that's what specialization refers to. That is, from the general, find some specifics. Okay, so some specific cases. So those are the subgroups. The flip side of specialization, the other side of the same coin, the other way of looking at the same thing is from the bottom up. So specialization, you saw in the discussion that we just had, we started from account and said, oh, an account has different types of subgroups. Okay, and these subgroups share certain characteristics that are above here, but there are certain attributes that are not common across the subgroups. All right. Now, generalization is a bottom-up approach. So I could first think of the subgroups. So there's checking account. I could think of a savings account. I could think of a loan account. Okay. And if I think of those three things separately, sure, I will notice attributes that are different across those three types of account. But immediately I will notice that, hey, these three different types of accounts share certain things in common. So what I could do is I could take the attributes that are in common across these three groups and move them out from each of the subgroups to the one on top, and I end up with the same structure, okay, that we had when we looked at specialization. So generalization and specialization are two different ways of looking at the same thing. Okay, one is a top-down approach, and one is a bottom-up approach. The terms are basically conceptually equivalent. Okay. So now that we have had a discussion of the business circumstances that gives rise to these subgroups, and we saw some example, the technical term for this generalization and specialization that is associated with the entity relationship modeling process is supertype and subtype. And I think you can guess what these two terms refer to. The picture that we had, for instance, we had account on top, and then we had three different types. We had checking, we had savings, and we had loan. Okay, so these three are the subtypes, and this guy is the supertype. Okay, the common attributes when we're grouped together, that's the supertype, and the specialized, the subgroups are the subtypes. Okay, and remember, relationships are always represented by lines. So these lines connecting the supertype and the subtype, these lines, their relationships always have a name associated with them. These connections between the supertype and the subtype is called an is-a relationship. Okay, so a checking account a is a type of account. A savings account is a type of account. A loan account is a type of account. Okay, or you can go in the reverse direction. The account, the generic account is consisting of different subgroups: checking, savings, and loan. So this relationship between supertype and subtype is referred to as an is-a relationship. This is just a naming terminology that is associated with the diagrams that we're about to build, okay, that will go into and become part of some entity relationship diagram. Okay, let's see a specific example or two specific examples of the subtype, supertype, and we'll reinforce some of the concepts that you have just introduced about specialization and generalization, and we'll also add some more concepts. You can see symbols over here in this picture that we have not discussed so far. So let's see how to read this diagram. First of all, in this diagram, you can see boxes, and we know by now that boxes represent entities. So let's just look at the example on the left-hand side. So we are dealing with this entity student. So we see this box called student, right? And then there are this attributes, last name, first name, and something called whether the student is a graduate student or not, all right? Now, just below student, you see two boxes also. So as soon as you see a box, it should suggest to you that it's an entity. So we have undergraduate and graduate, but notice that these two boxes have curved ends, edges, corners rather. Okay, so the suggestion to you would be, yeah, these are entities, but maybe it's like there's some nuance to them. So these are your subgroups. So if you look at this picture as a whole, you can think of this as a decomposition of a box called students. You had a box, an entity called student, and I'm trying to represent it now in a more refined way. So what this picture is telling me is that this supertype called student has two subtypes. One is an undergrad student and one is a grad student. Okay. Now, what are some of these other symbols over here? You have this circle with an X on it and a line underneath it. And then I already discussed what the rounded corners are supposed to signify. They're supposed to signify that these are subgroups. Okay. Now, what this X in the circle connects the subgroups to the subtypes to the supertypes, right? So what does the X on this circle represent? The X stands for exclusive, meaning the two subgroups are mutually exclusive. A student cannot be both an undergrad and a graduate student. Okay, and that's why we have the X in it. So either a student is an undergrad or is a grad, and the attribute that will tell us which subgroup to subtype to use is this attribute called is grad student. So this attribute called is grad student is a yes/no kind of flag, and it tells me, it's called a discriminator. It tells me this: if I look at a particular student, if I have a student ID, and I know whether the student is a grad student or not, I immediately know which subtype I'm talking about. So this entire tree structure that you're seeing is an example of a subtype supertype structure, and this is a situation where you have exclusive subtypes. In other words, an instance a student, so an instance of this entity class, one particular student can either be an undergrad or a grad, but not both. That's what the X signifies. Okay. Now let's look at the second example on the right. This is again a subtype and supertype. So you can see these two boxes with rounded corners telling you that they are subtypes of the supertype student. But this time, the structure called structure over here represent club membership of different students, okay, not their graduate, undergraduate status. So a student could be a member of a hiking club or a sailing club. Now, a student could be a member of both, okay? So these two subtypes, the hiking club, so the instances of hiking club, is if I were to dig deeper and I looked at all the students who are members of this hiking club, if I looked at all the students who are members of the sailing club, I might see overlap between the two. So it is not exclusive. The subtypes are not exclusive. They're actually inclusive. Hence, you don't see the X. Hence, you don't see the X. But in both cases, do you see that there is a single bar underneath the circle? And that has some significance. We'll see that in just a moment. But I hope for now you understand what the X means and what the circle tells us and what we mean by exclusive subtypes and inclusive subtypes. Okay, so this slide over here simply tells you in words what I just described. For now, I find it easier to describe it with to look at the diagram first, and then I can go over this particular slide. So specialization. Okay, when you go from the supertype to the subtype, when you specialize, when you go downwards, okay, it's a top down that you're going. Specialization can be exclusive disjoint. Okay, exclusive means the disjoint subtype, the two subtypes, or the subtypes don't overlap. Okay, or they could be inclusive, or they could be overlapping, like you saw in the case of the sailing club. Okay. And if it so happens that the subtypes are exclusive, like you had for the grad undergrad status, there is usually an attribute in the supertype that tells you what will put the student in one of those groups. So there is what is called a discriminator. Okay, it's an attribute which indicates which one of the subtypes is appropriate for a given instance. So the absence of a discriminator signals inclusive or overlapping subtypes. So that's just a textual statement of what we had just discussed with these two examples. Okay. So the bottom line is this tree structure, this supertype, subtype structure that you're seeing is simply a refinement of our concept of an entity, okay, to capture more nuances about entities that are typically present in real life applications. So this has not been introduced just to introduce complications. They help us model the structure of real life data. One last refinement to introduce to you is specialization. Remember, we said specialization and generalization are essentially conceptually the same thing. They're two different ways of looking at the same thing. So specialization can be either complete or partial. So if you think back to the two examples that we saw a minute back, or the distinction that we spoke about between these two examples is one is exclusive and the other is inclusive. So it's non-exclusive. Okay? So exclusive means the subtypes do not overlap. They are distinct. They are exclusive. They're mutually exclusive. In the case of the sailing club, the subtypes are inclusive, meaning there could be overlap between the subtypes. Now remember, in this example, there are only two subtypes. You could have a supertype that has 3, 4, 5 subtypes. There's nothing magical about the number 2. It just so happens, for instance, you have the hiking club, sailing club, and you could have some other club, rifle club, or some other sports club, all kinds of clubs. Okay, so there could be more than 2 subtypes we see over here. Now, the one thing I mentioned to you is I asked you to notice that in both these two, the distinction between these two trees, one has an X, the other doesn't. But in both cases, you have a single line underneath that circle. Okay? So that's what we will focus on next. That is, specialization can be either complete or partial. So what do we mean by that? Okay. So, complete means that every instance of a supertype has a related subtype. Partial means an instance of a supertype may not have related subtype instances. So that's a fancy way of saying something that we all understand. Yeah, so let's come back to these two examples that we are seeing over here. Why this? So if I think of a particular student, so I pick any student at the university. Okay. Sure, most of the time when I pick a student at random at the university, so I pick a student in the super type, the student is usually either an undergrad or a graduate student. Okay, and that would probably cover 95% of the students. But just think about it, it doesn't cover 100% of the students, right? Why? There could be non-degree students, there could be students that are just taking a course or two, they are not in any undergraduate program or any graduate program. So you could have a student who is neither an undergraduate nor a graduate. All right. So to use these two terms, the the specialization, the specialization of student into undergrad and graduate is incomplete. So you could have a student who does not belong to either group. All right. Now, if you have a university, for whatever reason, the university has a policy that in order to be a student at the university, you must be either an undergraduate program or an undergraduate student or a graduate student, then we would say that the specialization is complete. So every student belongs to one of or the other of these two subtypes. In that case, we would put a double line underneath this circle. Okay. So that's the distinction between complete and partial specialization. Okay. So this rather detailed discussion that we have had about generalization and specialization, just sort of refinements of our concept of an entity, these are the symbols that are associated with the discussion, the narrative that we've just had about the generalization and specialization. So you could have a circle with an X on it with two bars at the bottom. If you see this symbol, what does it mean? It means that the specialization simply means you have, where's my pen? Specialization simply means you have a supertype and then you have subtypes below it. That's what specialization means. So this little box over here, it could be any one of these. And these pictures tell different stories about the nature of the specialization. So let me pick the laser pointer again. So this entire tree is the specialization. So you have a supertype and subtype. So the specialization is of four different types. You have these symbols in the middle. You could have a circle with an X on it and then two bars. Two horizontal bars means the specialization is complete, meaning if I look at any instance of the supertype, it must belong to one of the subtypes. So the specialization is complete. Exclusive means if I pick an instance of a supertype, it belongs to one subtype and one subtype alone. There is no overlap between the subtypes. Okay. Alternatively, the picture that you see in this middle over here could be a circle with an X through it and just a single horizontal bar. That means the specialization is disjoint but partial. Disjoint means if I pick an instance of the supertype, it belongs to one subtype and one subtype alone. It cannot belong to multiple subtypes. However, there could be instances of the supertype which do not belong to any subtype. So the specialization is incomplete. There are instances of the supertype that don't go into any of the subtypes. Okay? And the example that I gave you is the university where there are students who are neither undergrads nor grads, they're just taking courses. Okay? And the third symbol that you could have a circle with no X through it. So it's overlapping but complete. What that means is if I pick an instance of the supertype, it may belong to more than one subtype, okay, but it'll belong to at least one, okay. So the specialization is complete. you never have an instance which does not belong to any subtype. So that's overlapping and complete. And if you see a circle with no X on it and just one single bar, that means it's overlapping and partial. So these are the four different symbols that you could see in this middle box over here. And those are the four sort of variants of specialization that you could encounter in an entity relationship diagram. Okay, so let's see a little narrative and discuss how it translates into a particular specialization structure. Okay, so in the narrative it says all food products. It says all food products sold by a grocery store have a product code, name, and unit price. Okay? For products such as fruits and vegetables, additional attributes are tracked to determine whether refrigeration is required, number of days the items can be kept on the shelf, number of days the item can be kept in storage, and so forth. For frozen items, data tracked includes whether it's a prepared food or not, whether it contains meat, the days it can be kept in the freezer. Other packaged foods such as coffee, tea, and snacks, tracking includes hard packaging or not, whether it contains any nuts, whether it contains any gluten, and so forth. Okay. So you can see that certain food products all food products have certain properties in common, and then some food products have properties that depends on the category that they're in. So let's see how, if you have this little narrative. So this narrative that you see over here is an example of something that you might get in the description of the business application. So this is sort of analogous, that little airline description narrative that we had as one of our examples in the previous discussion. So imagine that you encounter this narrative telling you something about how the business operates. What would you capture from this narrative as the underlying data structure, the structure of the data corresponding to this narrative over here? First of all, you have this super type of food. So this grocery store carries all kinds of products. And what this box on top is telling you is all food products, regardless of their category, have a product code, have a name, and they have a unit price. So that's the super type. Okay. Now, if you look at the bottom over here, those are the three different subtypes, okay, so our specializations that seem to come out from this narrative. So if you read the narrative, those are the three categories of subtypes of food specialization that seem to come out. One of them is produce. So this is, it says here, for produce such as fruits and vegetables produce, there are frozen food, and there's packaged food. Okay, these names, every entity must have a name, that you know that by now. These three names are sort of extracted from the narrative that you have over here. And if you look at the attributes for produce, it's whether it's refrigerated, yes, no, what is its shelf life, what is its store life. For frozen food, whether it's a prepared food or not, does it have meat, how long can it be kept in the freezer. And for packaged food, you have other things which says, is it a hard package, does it have nuts in it, is it gluten, So you can see that for the subtypes, the specializations, the attributes are not shared, they're not common. That's why we broke them up into different subtypes. But there are certain attributes that are common to all food products, and that went into the super type. Now the important thing is this symbol in the middle over here tells us the type of specialization. So if I look at this conglomeration as a whole, this T structure as a whole, that's the specialization. But this symbol in the middle tells us something more about the specialization. Okay. So first of all, this circle, you'll always see a circle that tells you that's the specialization. And you're seeing an X through. X stands for exclusive. What that's telling me is a food product can be a produce, it can be frozen, it can be packaged, but it can't be in multiple categories. It's either one of these three. It can't be in multiple subcategories at the same time. So you can't have a food product that is both produce and that is also frozen. Okay, that's what the exclusive tells me. Now this single line at the bottom of the circle tells me that this specialization is incomplete. All that means is there could be food items that are not in any of these three subcategories. So there are food items that are neither produced, nor frozen, nor packaged goods. That's what this single bar means. That's the incomplete. So this is exclusive. So for disjoint, incomplete specialization. That's the kind of specialization that you see that corresponds to this narrative over here. So if you had to draw an entity relationship that captures the structure of the data underlying this business application, this is the picture that you would come up with. And somebody looking at this picture would immediately get a sense of the structure of the data of this particular entity called food that corresponds to what this particular business is doing. Notice that the structure of the specialization would depend on how the business operates. So it's very much dependent on your knowledge of the business application. Okay. Now let's look at this example with students that we have discussed prior also, and introduce variations of the circumstances and see how that would affect the diagram, the entity relationship diagram of the specialization. So this structure that you see, this tree structure that you see, is a specialization of students. So we are taking the entity called student and representing it in a more specialized manner. So you have this super tag called student, and then you have subtypes called undergrad and grad, and then you have this symbol in the middle. The critical thing is this symbol in the middle that tells you the nature of the specialization. Okay, so here you have a circle with the X and you have two bars, right? So even if I don't read this narrative, I'll read that in a minute, but even if I don't read that narrative, what this symbol tells me right off the bat, this X tells me is if I pick a student, any one student, the student has to be either an undergrad or a grad, but not both. That's the exclusive. And this double bar tells me that there cannot be a student who's not in either of these two categories. So it is complete. The specialization is complete. That's what those two double bars represent. And it's exclusive. That's what the X represents. That's what this picture as a whole tells me. Okay. So he said every student is either a grad student or an undergrad student. The super type is student. The subtypes are grad student and undergrad students. Okay. So it is disjoint complete. This particular specialization is disjoint complete. That's what the picture is telling me. Now let's change things around a little bit. So here we have a slightly different situation. So every student is either a graduate student or an undergraduate student. However, some undergraduate students are admitted to a graduate program and begin taking courses before they complete the undergraduate degree. So again, this is something that a particular university is allowing to happen. There's nothing magical, there's nothing sacred about it. It's just the way a particular university operates. That's what the narrative is telling us. So whatever data structure we come up with is very much dependent. I'm saying this repeatedly just to drill it into you, that the database structure that you come up with must reflect the business application that you're trying to support with the database. So you must understand the characteristics of the business application. So here the narrative is telling me, sure, you have a student who's either a grad or an undergrad. However, there could be some undergraduate students who are admitted to a graduate program and they begin taking graduate courses before they complete the undergraduate. Now, given this narrative, what does this specialization structure look like? Again, you have a super type called student, you have undergrad and grad, the two subtypes, but notice that this symbol in the middle has changed. Okay, so again, you have two horizontal bars that tells me that the specialization is complete, meaning if I pick a student, I will find that student either here or here, but now I don't have the X. That means it's not exclusive. So I could have a student who is both an undergrad and a grad. Okay, so this is overlapping but complete. So this is an overlapping specialization but complete. So it's not disjoint. It's an overlapping specialization. The two subtypes overlap, but the specialization is complete. You don't have a student, you cannot have a student who is not an undergrad or a grad student. That's what those two double bars represent. So pictures always tell a story. There are no superfluous, no redundant. You don't put symbols into an diagram for nothing. Every symbol tells you a story, and it has to reflect accurately what's happening in the business application. Okay. Now this is one more variant. If you compare to what we saw before, the previous one we had student, undergrad, grad. This is the specialization, this tree structure itself. And again, notice the symbol in the middle. There's a circle with two bars below it. Okay. So what has changed now? A lot of the picture is the same. You have student. This is the super type. The two subtypes are undergrad and grad. And if you look at the symbol in the middle, you again have a circle without an X on it, but now you only have one horizontal bar. So how would I interpret this? The way I would interpret this is, I have a student, okay, so there's no X in the middle. So the two subtypes are not disjoint, they're overlapping. There could be a student who is both an undergrad and a grad. That's possible. That's what this structure is telling me. So the two subtypes are not disjoint, they're overlapping. However, now that I see this single bar, there's no double bar now. What this single bar is telling me is that this specialization is incomplete. So if I took a student, I cannot categorize them into one of these two. So there could be a student who's neither an undergrad nor a grad. So the specialization is overlapping and partial. Okay, so it's not complete. That's what this picture is telling. So just these little slight differences in the picture that you see, that the symbols that you see, tell a vastly different story of what is happening underneath in the business. Okay, to summarize what we have discussed, we've taken our basic concepts of entity relationship diagram, namely what are entities, what are relationships, cardinalities, and so forth, and we've added some more refinements and some more concepts, some more symbols into that to allow us to capture real life data structures more accurately and more faithfully, and therefore hopefully it'll do a better job of supporting the business application. What are some of the new things that we have discussed and introduced in this particular lecture? We talked about relationship attribute, that is, some attributes are associated with relationships. We have said before that it is very natural and easy to think about attributes of entities, but relationships themselves can have attributes. So these attributes are not properties of any one of the entities involved in the relationship, but they are attributes of the connection, the relationship between the entities. The examples that we had were grade and shipment of couriers and so forth. Okay. Uh, Then we talked about the degree of a relationship. As I said, 90% of the time you'd be encountering binary relationships. The degree of a relationship is associated with how many entities are involved in the relationship. So as I said, 90% of the time you will have two entities involved in the relationship. However, there are unary relationships, there are ternary relationships, there could be quaternary relationships as well, but those are very, 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 very infrequent. As I said, 90% of the time, the degree of the relationship that you will encounter is a binary relationship. Maybe unary, even ternary is not that common. Okay. Now, generalization and specialization was another refinement that we introduced in this lecture. This is a way of organizing subgroups. This is a refinement of our concept of entities. So sometimes in business setting, entities are organized very naturally into subgroups, and this concept of generalization, specialization, and disjoint subgroups, incomplete subgroups, complete subgroups. These concepts and the symbols associated with them allow us a good way of representing those structures in the entity relationship diagram that will capture the structure of the database. So these are all the things that we have covered in this particular lecture.